Please enjoy this completely unrelated image that I found in Microsoft's stock portfolio. Okay, let's talk graph theory. So what we're essentially looking at here is chapter 2. And the reason that we leave chapter 2 until practically the end of the whole course is because it's very dull. A lot of it is putting definitions of things together, and it's much better to get a feel for those definitions by using them and then coming back and sort of summarizing everything. So that's what we're going to try and do here. We're going to try and summarize the things that you should know about graphs, aka graph theory. So let's start. Now I'm going to essentially rattle through these because we've used them, but let's talk exactly what we have here. So let's start with node. So node, all you really need to think about that as a definition is its points on a graph, and arcs or edges are simply the lines that connect nodes. Order or degree or valency is something we came up against in the Chinese postman algorithm, and it is the number of arcs from a node. And then weight is obviously the cost of an arc. So that could represent a lot of things. Normally we're talking something to do with distance. So if we draw a sort of classic looking little graph here, there we go. We can see that the nodes are clearly highlighted in red. We can see that the arcs are clearly highlighted in black. We can see that the weights are clearly highlighted in green. And then the orders, let's put them in purple, will be the number of arcs going from a point. So the order of this node here is just 3, because there are 3 arcs coming from it. Order there is 2, 3, and 2. Now they might use the word degree, they might use the word valency. Look out for those. And then we have a list of very similar words that are slightly different to each other. So let's use this little graph to do our illustration. We'll start with walk. Okay, so a walk is basically any route through a graph. So in this example, we could have A, B, C, B, A, B, E. It is not necessary to visit every vertex. It's not necessary to only go to one place once. It's any little path you want to take through a graph. A slightly more strenuous version of that is a path. And a path is any walk where you don't visit a vertex more than once. So we could have A, B, C, D as a path on this particular graph. Again, no requirement to cover every vertex or every arc, just a walk where we don't go to the same place more than once. We can upgrade that slightly now to a trail. A trail would be any walk where no edge is visited more than once. So for a path, we couldn't visit a vertex more than once. For a trail, we can't visit an edge more than once. And to be honest, we could use A, B, C, D again there. I'm not using the same edges twice. What about a cycle? Well, a cycle is any walk where you end at the same place that you start. And you don't visit any other vertex twice. So we could have A, B, C, D, E, A as an example of a cycle on that one. We've used cycles in terms of prims and cruscals in terms of not having them. And we've also used them in terms of the traveling salesman problem, specifically when we started looking at Hamiltonian cycles. And a Hamiltonian cycle is, so that's a cycle where you visit every vertex. So realistically, if we want to have a difference here, I could have my cycle as being just something like B, D, E, B, because that goes back to the same point that you started. But a Hamiltonian cycle would need to cover every single vertex on the actual graph. And lastly, there's a loop, and a loop is just any arc that connects a vertex to itself. And the graph above obviously doesn't contain any loops, but there's a drawing of what one might look like. Okay, so another few definitions. So a simple graph is any graph that doesn't have any loops and doesn't have multiple arcs between the same pair of vertices. So if we were to consider these 3 graphs here, The first one wouldn't be simple because it has got a loop. The second one wouldn't be simple because it's got multiple arcs. The third one would be simple. After that, we've got a subgraph. And a subgraph is basically the idea that you take an existing graph, you remove some edges, maybe some vertices, and that's a subgraph. So if we started with the complete graph above it, there are 3 examples of subgraphs that we could get if we just took some of the arcs and vertices. Okay, and then we go on to connected, and there's kind of 2 definitions for connected. So 2 nodes are connected if there is a path between them, but a graph is connected if every node is connected to every other node. So in our 2 little examples there, the first graph is connected. It's possible to get from every node to every other node. The second graph is not, because this graph has been cut off, or this node has been cut off from the other 3. And lastly, we've got the definition of isomorphic. So isomorphic essentially means that 2 graphs are the same as each other, or could be like translated into each other. So those 2 graphs I've drawn there don't look similar, but if you were to replace E with A, F with B, G with C, and H with D, you would find that the nodes are connected to exactly the same nodes as they were in the previous graph. So as far as we're concerned, we can treat those 2 as being exactly the same. We don't really do much with this in decision, but you still might be asked to prove that 2 graphs are isomorphic to each other. Then there's trees. Now trees are something that we looked at with prims and cruscles because we're interested in making spanning trees. But what's the actual definition for them? So it's a connected graph, so you've got to be able to get from every single node to every other node, and there's no cycles, so it's impossible to do a route where you end back where you started without visiting the same vertex twice. This is an example of a tree. If I was to add in that arc there, it would no longer be a tree because there will be a little triangle cycle there. Something that doesn't seem to be on the course, but I quite like as a fact, that if a tree has n nodes, then it always has n-1 arcs. So you can see on that example I drew, it had 6 nodes, but it's got a total of 5 arcs. And a spanning tree is it's a tree that is a subgraph of a larger graph that covers all of their nodes. I'm not going to draw an example of one of those, but just see your notes on prim and cruscle. A word that I don't think we'll have encountered yet is planar. And a graph is planar if you can draw it without any of the arcs overlapping each other. So if we were to look at these 2 graphs, well, it's obvious that the one on the left is planar because we have drawn it with no overlapping arcs. And you might be tempted to conclude that the one on the right is not planar, but it actually is, because we could redraw it so that this arc that goes top to bottom instead goes around outside the shape. You're allowed to use like isomorphisms. So it's not just that your graph has overlapping arcs, it's that it's possible to draw it without other overlapping arcs that makes it planar. Region is a very linked phrase here, and it's just sort of an area enclosed by arcs on a planar graph. So if we were to take the graph we just drew that was planar, how many regions do you think this has? Well, it's definitely got 1 here, then 2, then 3, and the outside counts as well. So there's a total of 4 regions to that graph. Something that we've heavily used in Chinese Postman algorithm is Eulerian and Semi-Eulerian. It's probably worth making sure we've got those definitions written down along with the rest of our graph definitions. So Eulerian, as you'll remember, is a graph where all of the nodes have even order, and it also needs to be a connected graph because we want to visit all of the streets. And a Semi-Eulerian graph is a connected graph where exactly 2 of the nodes have odd order. So if we were to look at the orders on our first graph here, they're all 2, that makes it Eulerian, whereas on this one 2 of our nodes have order 3, which makes it Semi-Eulerian. So we can then have a complete graph, and a complete graph is one where every node connects to every other node twice. You can see here we've got 4 nodes, and they're all connected to each other. This is actually the graph known as K4, because it's a complete graph, which apparently we're using K to stand for now, and it's got 4 nodes. So you can see here we've got Kn, that's a complete graph on n nodes. So you can see there we've got K3, K4, and K5. Incidentally, I think we proved K4 was planar a couple slides ago. K5 is not, and that is an interesting proof to go through, but not one that's on our course. Lastly, 2 more definitions. So we've got a digraph, which stands for directed graph, as in a graph which has got directions on the arcs, and we briefly considered them with, I think, the Floyd algorithm. And lastly, there's Euler's handshaking lemma, which is the greatest possible name for something that's so very simple. And that observation is that in any graph, the total order, so the sum of all the orders of all of the nodes, is 2 times the number of arcs that that graph has. Now we can sort of check that with, say, our K3s up here. So our K3, our orders are 2, 2, and 2. Total order is 6, and the number of arcs is 3. 6 is 2 times 3. Yeah, that works. Okay, what about with the K4? So the orders are 3, 3, 3, and 3. So the total order is 12, but there are 6 arcs. So yeah, it works for that. And you'll find for K5 that's also true, that we should have a total order of 20, but only 10 arcs. Does it work for our digraph? Yeah, it does. We've got 2, 2, 2, and 2. Total order is 8, but there are 4 arcs. So yeah, that's our definitions. So there is an absolute ton of questions that they can ask you to do with graphs and those definitions, but I thought I'd look at some of the ones that certainly were more common in the old days. So firstly, we need to explain why it's impossible to draw a graph of orders 1, 2, 3, and 3. This is a great instance of Euler's handshaking lemma, because if we add up all of those orders, 1, 2, 3, 3 equals 9, that gives us our total order, and that would tell us that there are 4.5 arcs. Now that's obviously impossible, because you can't draw half an arc. An arc has to connect a node to a node. It's either there or it's not. Second question, explain why there is no simple connected graph of orders 1, 1, 2, and 4. So simple obviously means that we can't have any loops and we can't have any multiple arcs. So let's say multi-arcs. A connected graph means that every node needs to be able to connect to every other node. So what's the problem here? Well, the problem is the 4. If we sort of label up how we want this to work, then that 4 node can connect to all 3, but then it's kind of got a problem. If it wants to get to order 4, it needs to either connect twice to something, or it needs to connect back to itself, but there's no way that that can be drawn simply. So our answer would go something like, firstly, an acknowledgement that the maximum simple order we could have would be 3, and then stating specifically that that 4 node must have a loop or multiple arcs. But fear not, it's not all proving things don't exist. Quite often you are asked to draw a thing matching some specific criteria. So we want to draw a connected graph with 4 vertices of order 2, 2, 2, and 4. So I draw them, label up the orders that I want to get out of here, and it's connected, so they all have to connect to each other. So I could do something like this. That would work. It didn't say it's simple, so I'm allowed to use loops. Yeah, the orders match up, it's connected, we're done. How do we know the graph is Eulerian? We know the graph is Eulerian because every node has even order. Simple as that. Similarly, we want to draw a non-Eulerian graph of orders 2, 2, 2, and 4. So, well, surely that is Eulerian because all the orders are even. But remember, there are 2 parts to the Eulerian definition. It's not just that all the arcs have even order, it's that it's connected. So we could, for example, do something like this. there we go. That's a non-Eulerian graph because it's got the correct orders, sure, it's got 2 and 2 and 2 and 4, but there's no way of connecting them together. Okay, slightly longer sort of question here. What's the minimum number of arcs that a simply connected graph of 6 vertices can have? And draw an example. So, as with all these questions, I'd recommend sticking the nodes down first and then thinking about what they're going to connect together. So it has to be connected. We can't have any loops, we can't have any multiple arcs. We want the smallest number of arcs possible. That is going to be a tree. So there's an example of something you could draw. There are lots of other trees we could draw. So the minimum number of arcs we could have would be 5 arcs. Remember, a tree on n nodes has n minus 1 arcs, so 6 vertices will give us 5 arcs. What is the maximum number of arcs you could have? Well, maximum is generally defined as a kn graph, or a complete graph. Again, we're assuming it's still simply connected. So what we'll do is we'll draw ourselves a K6, which I believe forms a little bit of a pentagram, but we won't get too hung up on that. Yeah, there we go. How many arcs does it have? Well, the total order of that is going to be, well, each of these has order 5 because they connect to the 5 other arcs. So the total order is equal to 30. So the total arcs, remember Euler's handshaking lemma, is half that as 15. You could also add them up, I suppose. What's the maximum number of arcs you could have if it was also Eulerian? So if it's Eulerian, that obviously means that the needs to stay connected, needs to stay simple, but we can't have order 5 anymore. We're going to have order 4, maybe. So that would be the best case scenario. Can we make that actually happen? Yeah, hopefully, I think we can. So if we go like that, and like that, yeah, we end up with a little 4-degree node for every single vertex. That'll work out. What's the maximum number of arcs there? So we need to do again the Euler calculation. The total order is equal to 4 times 6 is 24 this time, and so the arcs would be 12. And lastly, what's the maximum number of arcs it could have if it was semi-Eulerian? And draw an example. So semi-Eulerian means 2 of the graphs can be of odd order, and so our first hunch would have to be to try and increase the order from what we had. So we'll try 4, 4, 4, I guess 5, 5, 4, 4, because then we can use the graph that we already had. Let's draw that a little bit better. And we can also connect together the 2 5s. And yeah, that works out. What's the actual number of arcs there? Well, total order is 4, lots of 4, 16, 2 5s makes 26. And so we've drawn there 13 arcs, which makes sense because it's 1 more arc than we had in the previous question. So yeah, loads of graph definitions and a few questions to try.